Hey everybody, this is Beej with Lambda School, and today we're going to be talking about the CPU stack. The goal today is to learn what the CPU stack is and to see how it's used. So we'll cover that stuff, and we'll also look at why it's important. So what is the stack? Right now you should be thinking, I know what a stack is. I've already learned this. The stack on the CPU is very much the same. It has the exact same operations that you know, such as push and pop. We need a place for that stack to store its information. You're used to probably allocating something for that, but we're just going to continue to use RAM as it exists. And then we need a way to keep track of the top of the stack. And we're going to use the stack pointer for that. The stack pointer is sometimes a special purpose register, sometimes it's one of the general purpose registers that's been reused as the stack pointer. Now commonly on a CPU, the stack starts high in memory, at high memory addresses, and then it grows downward. So it'll start high up and grow downward. This is different than the program, which usually starts at a low memory address and is loaded upward. So the stack grows down towards the program, and hopefully they don't collide. If we do, we have what's known as a stack overflow. So once again, what do we need for our most minimalist stack? We need a place to store things that we push on there, so we're going to use some RAM for that. We need to keep track of the most recently pushed item on the stack, so we know what the top of the stack is, and we'll use the stack pointer for that. And then we also need our push and pop functionality, and that's all. This is our minimum stack. So really, we've already got the RAM set aside. All we need is a stack pointer, and then to implement the push and pop functionality. So let's run some examples of a stack here. And we'll push some values on. We want to push 12 and then 7F and then 37 on there. These are hexadecimal values. We see in the table on the left, we've got addresses. And of course, this isn't all of memory. This is just a little window of memory here that runs from address E9 up to address F4, shown at the top, also in hex, obviously. And the values that are stored in those addresses are in the right column. Currently, everything's 0. Right now, the stack pointer points at address F4. That is, the value inside the stack pointer register is F4. So the value inside the stack pointer register is going to be the index into our memory array. And so what do we want to do when we want to push a value? The stack pointer is going to start off initialized to a certain address. The spec will say which one. And then the spec will also say for a push instruction exactly what has to happen. In this case, what we're going to do is we're going to decrement the stack pointer, and then we're going to store the value in question at the address pointed to by the stack pointer. So if we want to push the number 12 onto the stack, the first thing we do is decrement the stack pointer. So now it points to F3 instead of F4. And then we're going to take the value 12 and we're going to put it in memory at the address pointed to by the stack pointer. The stack pointer points to F3, so let's take the number 12 and put that in address F3. There, we've successfully pushed the number 12 onto the stack. Notice the stack pointer is pointing at the most recently pushed item on there. So let's do the same thing again. Let's push 7F onto the stack and see what happens. Same procedure. First, we decrement the stack pointer from F3 to F2. Then we want to store the value 7F at that address. Now let's push 37 on there. Same procedure. Decrement stack pointer, store 37 at that address. And so you see we have our stack. It is growing downwards towards our program, which is shown off screen somewhere, way down at address 0, 1, 2, and 3, and so on. But we've got 3 items pushed on there. We push 12, 7F, and then 37. Let's take a look at the opposite, pop. Now, when we pop a value, we need to store it somewhere. There's no point in popping it and just throwing it away typically. So what we're going to do in this example is pop into registers. So we have 2 arbitrarily chosen registers here, register 0 and register 1. So I'm going to do a pop instruction. I want to store the result of what's at the top of the stack in register 0. So I want to pop this value 37, and then I want R0 to be set to 37, after we do so. So this is just like push, except we're going to do the operations in reverse and we're going to move the stack pointer the other way. So the first thing we want to do is take the number that's stored at the top of the stack, namely 37, and we want to copy that into register 0. So register 0 now has the value 37. After that, we wish to increment the stack pointer so it goes from F1 to F2. Now, if we want to pop into R1, we do the exact same thing. So we take 7F at the top of the stack, we copy that into R1, and then we increment the stack pointer again. So what we have here is a case where we've left stuff over on the stack. We have 7F and 37 are still on there, and that's okay. CPUs typically don't remove that stuff from the stack. They just leave it on there. Next time we push, it gets overwritten, and that's fine. It would take extra time to change it back to 0, so the CPU typically doesn't bother. So how is the stack used most commonly? Well, one of the common things to do is temporarily store variables there. So let's say you're using registers to do some math, but you've run out of registers because you only have so many at your disposal, but you've calculated some intermediate value that you need to use later. Perfect thing to do is push it on the stack, then reuse that register for other things, and then pop it off the stack when you're done. Another common thing to do is store the return address from a subroutine. If you're doing instructions like call and return, call will jump to a different part of the code and will run some different functionality for a while until it hits a return instruction, and then it'll jump back to whatever it was doing before. Subroutines are just like functions in other languages. When you call a function, you expect the code within the function to execute, and then you expect to be returned to exactly where you were before you called the function. And so in order to keep track of where to return to, the call and return instructions will store the return address on the stack so that return knows where to go. Similarly, if you have interrupts on your CPU, whenever an interrupt occurs, normal processing has to stop and the interrupt has to be handled, and then normal processing has to resume. In order to resume that processing, what we do is we save the entire CPU state on the stack. So we save all the registers, all the flags, and then the interrupt is handled, and when the interrupt returns, all the registers and all the flags get restored, and then the CPU continues where it left off. Another use for this, commonly used from higher level languages like C, is subroutine or function local variables get stored on the stack. So when a function is called, the stack not only gets a return address, but it also allocates some additional space on the stack to store all the local variables that are used within that function. And that's a convenient place to store them because when you pop all that off the stack, the local variables are effectively deallocated when you do that. So, as a parting challenge here, you can pause this screen and try to answer these questions. Test your understanding of stacks. Thanks for watching, and we'll catch you all later.